Yes, so what I had in mind to talk about this afternoon is a set of kind of more practical problems that we can approach using machine learning and artificial intelligence. So where is the clicker? There. And I think John mentioned yesterday that going into data science and machine learning, one of the key things to do is to ask the good questions. So we as geoscientists need to think about what are the questions that we have that need solutions, and what are the things that we need to do that we may be able to do better, either more efficiently or more accurately. So there is a question here to start with, and it's a big question. Can a computer learn to map stratigraphic architecture and the reservoir quality simply by training on the data that we have available? And we need to drill down into the components of this in order to address it. But you can certainly argue that it would be useful, because in a historical place like this, we can think about geology. In the past, it's been an excellent descriptive science, and also today now with these virtual outcrops, the ability to describe geology is advancing enormously. But in applied geoscience and petroleum geoscience and exploration, where I have a lot of experience from, we have some issues when it comes to using geology as a predictive science. And the example here is just one out of many examples I could have chosen. It's the Barents Sea in Norway. We drilled 116 exploration wells, and today we have two fields there. 3 more are under development. But if you look at the numbers more in detail, you see that there are 56 discoveries. That means that we found something, but in most cases not enough to develop fields. So what is wrong here? Why did we spend so much resources and found so little? And part of the problem in this case is reservoir quality. So then you can break the question down to why is it so difficult to predict reservoir quality in this particular area. And petroleum geoscience, when we want to do predictions, it is really hard, because we don't have a set of simple rules like they have in physics and celestial dynamics or things like that. Now they can predict the location of Elon Musk's car for the next 20 years. It's some simple equations by Newton 300 years ago. But in geology, we don't have that. And we have complex, multidimensional relationships between various components of the systems that we're studying. But what we do have in our advantage is a lot of data, which we have seen through this conference. So we have the excellent seismic that images our sedimentology and structural geology in a fantastic way, and a lot of wells with loads of different measurements from these wells in the form of wireline logs and core data. So then we can start zooming in to the question that can we use this subsurface data in combination with artificial intelligence to improve our capability of predicting reservoir quality. And people have defined machine learning before, and I will just quickly highlight a couple of points here. That machine learning is very different from physics, because we're just asking or giving the machine the capability of learning relationships between things by exploring the data from the data itself. So we're not hard coding any rules. So we don't explicitly program anything. And I'll be talking about the specific type of machine learning called supervised learning, which is what most people are using these days. And that is about inferring a function from labeled training data. And now we're getting to the point, because we want to find this function, because we'll show that this function will be useful for us once we know it. But we need labeled training data in order to find it. So what do we actually need? Features and labels. So the features are some form of measurement. It could be anything. And the label is some property, the value of some property. It could be a class or it could be a continuous variable that matches those features. And so if you stack up many rows of this, then you're in business and you can try out various machine learning techniques. And you'll find this model after some trial and error usually, and the model can be used on new data to predict new labels for you. That's my high-level version of this. And drilling down into our domain in subsurface geoscience, so what are our features? We can use the wireline log measurements as features, and we can use something we know from the core data as our label set. For example, permeability or porosity, lithology, sedimentary facies, or basically anything that we have numerical ground truth knowledge about. So that upper row there kind of resembles what is currently done in petrophysics. So machine learning can be an alternative to many petrophysics approaches. And in the second row, it's an example about using seismic as the features, but in that case, inverted seismic. So we have the elastical properties of the seismic, and that's our feature set. And again, we can obtain our labels from the core data, like lithology, or from the logs. The petrophysicists, I don't know if the only one has left yet, but they provide us with continuous properties through all the wells, which we can also use to train on. We don't only have to train on the core data. And in some cases, it's inconvenient to train on this inverted seismic data because we may not have it. To send it to some company that will do it for us, it will cost money, it will take time. So we see that it's also possible to just start off with the partial stacks and find the relationships between the partial stacks and the properties that we want to explore, like, again, porosity, permeability, facies, and so on. So these are three things we can do with machine learning. There's, of course, many, many more. I wanted to include some examples about petrography, but didn't find the time. But the key message here is that you need access to feature sets and label sets, and then you can start. So if we zoom into the first problem, this is a classification problem. So you just get access to your wireline logs, and in this case, it was facies associations defined by a PhD student of myself and Chris Jackson many years ago. And you give the machine the task of finding the function that maps from those wireline log responses to those facies association classes. And there's a vast number of algorithms that you can try out, and it is more easier accessible than probably many of you think to start playing with it. Of course, as many things, it's hard to do it really well, but to get going and playing with it, it's quite easily accessible. And that was a classification problem. And there's another set of problems. It requires different algorithms, but the idea is similar. Again, provide these feature sets, and your, in this case, continuous variable as your label. Here we have porosity measurements from core. And you find the function that will give you porosity data as output. And you could see in the last example, and also in this, that the output, you get it obviously for the entire well or the entire stratigraphy of interest that you used in your input data. So is it useful? Definitely yes. It saves you the burden of going back here. I'm a sedimentologist, so I've actually done this manual labeling of sedimentary facies from the wireline logs. It's not something you want to be doing. It's boring, and it's prone to error and subjectivity. And it is definitely possible to automate. I think it's almost a year ago, there was a contest with this topic here as a theme, and it was more than 50 submissions. So all the submissions are open source, downloadable from GitHub. And here we get this continuous porosity log as the output. So it's easy to get started, but it's important to take care and use our domain knowledge and expertise to quality control the results. So one way of quality controlling what we get is to plot the output as well logs, basically. And in these plots, the blue curve is what the machine predicted using some algorithm. The green and the red curves are what the petrophysicist made in the CPIs. It's total and effective porosity. And the points are the porosity from the core plugs themselves, which we were trying to match to train the machine to reproduce. And you can see in this example, and we've done loads of these, that the output of these machine learning models for use cases such as this is high quality. It is comparable to the quality that you get from your CPIs. And it is, in some cases, even better, and the efficiency is kind of orders of magnitude higher. And you can keep going through this kind of approach with all the properties that you want to explore, given that you have the training data in place. And so this next one is permeability. And for permeability, those of you who have done petrophysics know that it's normally something we do with a cross plot, porosity permeability cross plot. And we do linear regression on that cross plot, find a function. We apply that function to our porosity log, and voila, there's our permeability log. But that's a very kind of low dimensional solution. It assumes that you have a one-to-one match with porosity and permeability, which obviously there's not. And with this machine learning approach, you can predict permeability as a function of your wireline logs without using porosity at all. And as you can see from the example, you can do this with reasonable accuracy. And again, you check the ground truth, prediction versus ground truth match with your core data. And in the example that I will go through, we were fortunate to be able to train the models on the core database or catalog from Icron. And they have some pretty good sedimentologists, so I thought we can treat this as our form of ground truth. It is human-generated data, but we can use it for training purposes. So another way to measure the performance of the models is to do it more quantitatively. So the first one was qualitative visual inspection, but we can also quantify the match. And we do this with a confusion matrix. It was shown yesterday. I'll try to explain why it doesn't have to be that confusing. So on one axis, let's see, on the vertical axis of the matrix to the left is the true label. So this is what, in this case, Andrew Thurlow, I suspect, labeled the core with these labels. So we treat that as the ground truth. That's the best knowledge we have about the truth. And on the horizontal axis is the prediction. So this is what the machine gave us after it was applying this function that it found during its training. And so you can tell that if the prediction matches the true label, then we count occurrences along the diagonal. So the color coding is just colored by number of occurrences, darker blue for more. And if the machine makes a mistake, it counts in one of the cells off the diagonal. So this is useful in the sense that we can go and check that these mistakes that are typically made, and there are typically some mistakes, but do they matter? And in this case, you see it confuses the interdistributary bay mudstones with interdistributary bay heterolytics, which for some use cases might be important to get it right, but for other use cases, maybe it doesn't matter. So you can go back and say, okay, I'm happy with this. I'll just group those two, run it again, and I'll have a model that predicts that facies set with one class less with a high probability or high accuracy. But already here, the accuracy was 92.2 in the so-called F1 score. So I would say it's okay, and we can move on. For these continuous variables, we use regression. And it's a similar technique. We can quantify the accuracy by some cross plots with a measured property on one axis, the predicted value on the other axis. And if everything is perfect, everything lines up on the diagonal, and you can quantify the perfection by the R² score. And so with this study here for an oil company was actually using this as a part of the business, and it was not a research project. So we went through all the wells in the Barents Sea that go through the Cretaceous, all the ones that were available at the time. It's like almost 1-year-old study. And for this company, we predicted, it's Moeco, Oil and Gas Norge, by the way. We predicted shear velocity, porosity, permeability, and sedimentary facies. And we could measure the accuracy of each model. And once we were happy with this, suddenly we had access to a data set that was orders of magnitude larger than what we had from the beginning. It was very small sections of the wells are cored. So once you have such a large data set and you have quality controlled it and you can treat it as something reliable enough, then what can you do with this? As one use case, we tend to plot correlation panels when we do regional exploration, which is this part. But now you can make these panels, you don't have to plot gamma ray and sonic and color it with density, but you basically plot porosity and color it with facies. So it's much more accessible to a geologist what this means. And you are able to produce these logs for every well in the basin and explore the distribution of lithologies, facies, and rock properties throughout the basin. Obviously, you can also plot these properties distributed on a map, in this case with some histograms. And the vertical axis on the histograms there is porosity, but it could be also permeability. And we color-coded the histograms with the sedimentary facies. And this particular map, it reflects the property distribution in one particular stratigraphic sequence, and we could produce maps like this for all the stratigraphic sequences in both the Cobbe and the Snad formation. So it gives you a very good spatial awareness of your property distribution in the entire basin. Obviously, in exploration, you need to zoom into some opportunities that you find interesting, and then you can collect the data in the neighborhood that you think is relevant for that particular question. And so for a local area, we made a permeability depth plot, colored it with the facies types, and you can ask questions like how deep can I go and still expect reasonable permeability in my fluvial distributary channel sands. So basically you have access to a database orders of magnitude larger than what you started with that you can start querying and asking all sorts of interesting questions. So you can also look at one particular facies in one area of the basin and ask what is the property distribution in a certain depth interval. And I just plotted 4 different ones, 1,000 meters for each, and you can see how the property distribution and its skewness kind of changes with deeper burial. So in in parts of the world where your seismic data doesn't help you obtain these kind of properties, this is obviously very useful, and you can extract input that is relevant for your Monte Carlo simulator and volumetrics tools like GeoX, I'm sure many of you use. But when you do have the seismic, obviously you should use it. And in this project we did have access to some inverted seismic. So we built machine learning models that found functions that can map from acoustic impedance, VPVS ratio, and some additional engineered features, like obviously depth and some extra. But basically these are the main information bearers, and it maps to sedimentary facies. And the input is in 3D, and so also the output is in 3D. And you can do the same with the regression problem for those continuous variables, like the porosity and the permeability. And I mentioned that in most of this area, we didn't have access to inverted seismic. But then you can step back and see if you can build models that map from pre-stack data, no, not pre-stack, but partial stack data to rock properties. So this porosity cube here was generated with a 3D deep convolutional neural net from the partial stack data. So, yeah, there's another one, 3D opacity rendered volume of porosity. And you may say now that this is all well and good if you have tons of data, but what if you're exploring an area with limited data, like in frontier exploration? And then I would ask you, what would you do as a human geoscientist in that case? And I would assume that your answer would be that you would play the analog game, try out various analogs, ask what-if questions. And you can do the same here, because you can build your machine learning models from multiple places where you have access to some form of ground truth, and then do the inference in the area where you only have your partial stacks, and play the same what-if games. It's just that this approach makes that exercise more objective and also efficient. So, approaching the end of the workflow, what you have is basically a bunch of 3D volumes representing the different rock properties and fluid properties that you predicted on the way. And now we are getting very close to something that you can use in your decision making, be it in exploration, field development, or production. And you can see this cube that I'm turning on and off, that's one of those rock property cubes that the machine learning algorithm is outputting. And you can sample it into your 3D geomodel grid. So there's an obvious next step, which John Thurman highlighted this morning. What more do you need? You need the faults, and you need the horizons, and then basically you can automate building of that 3D grid as well. So we're working on this, and it's on the schedule for the APG Salt Lake City. So for those of you who make the trip to Utah in May, we'll have this to present as well. So to conclude, you need to try to answer those questions that you ask in talks. So, is the machine able to map stratigraphic architecture and quality? And I think yes, it can do both. And we can quantify the reliability of those mapping functions that we found with machine learning. We can use the output to explore the uncertainty of our reservoir quality predictions. Now we have the opportunity to use all our data. We used all the wells in the basin, all the core plugs, everything. It's kind of unsurmountable for any human being to try to do this on a basin scale. but now it's possible. And like many have said before in this conference, I don't think this takes our job away from us. It just takes a lot of tedious grunt work away, but I don't mind. And we can start using our creativity armed with all this data, and there's so much interesting geology to do on top of this. So thank you very much. And if there is no limited time for questions and discussions, then please get in contact online.
Yeah, so thanks, Eirik. There is plenty of time for questions. You were
Good.
at least 5 minutes ahead of schedule, so yeah.
I've got a question regarding when you said that you are able to predict the permeability without the use of the porosity saturation water.
Yeah.
So my question is, what dogs do you use at your input? And the second question, how do you quality check that you are having a proper permeability curve?
Yeah, I think I showed the quality check, and it also lists the input logs. So in this case, it was density, P-sonic, share sonic, neutron, deep resistivity, medium resistivity, the formation it belonged to, the depth, and the relative position in the formation. So that's that. And the quality check is, I didn't highlight that enough, but someone talked about it earlier yesterday, that there are different ways to blind test things. So you can take some data and put it to the side. The machine never sees it during the training stage, and then the machine makes its prediction, and you compare with that blind data. So we tend to use those scores for the blind wells as our measure of accuracy, because that can be used in order to see how well your model will generalize to new data.
But you never had any perm data from labs in this specific?
Yes, all the blue points on the plot. Yeah. Yeah.
Yep.
A couple of slides on, you had your blind test performance.
Yeah.
I think it was very impressive. I think permeability is about 50%.
Yeah.
Was it a fundamental issue that you're not going to overcome? Or was that, say, a lack of relevance in your training data? What was the cause of that comparison?
It tends to come out kind of in this order. Share sonic is easy to get very high scores. Porosity also. Phases, if you just limit your classes and have actually phases that are different to each other, you can do well. And permeability tends to be a bit harder. So that's in our experience. Yeah.
Okay. Any other questions? Yep.
Was the pi for the Monte Carlo simulation, or you're trying to simulate the distribution of permeability, is that right? So is it 2 slides after or something, when you do the Monte Carlo? So you seem to assume some sort of distribution for your simulation or the input?
No, in this talk, I don't present that we did Monte Carlo simulation, but these distributions you can use as your input. You can use one of these, the one to the left, as your input to populate your Monte Carlo calculator. You can use that as input to GeoX. But these distributions themselves are just samplings of what is either observed or predicted by the machine in the wells.
So the figure is the prediction, or is it the one you use for the simulation? So these 4 figures, they are the prediction from the simulation?
They're the prediction from the machine learning model in wells. Yeah. But your prospect is not in a well, so you use input like that and Monte Carlo simulation to explore the uncertainty of what's in the prospect, where you don't have any measure of the truth.